handout I gave you to work with is what we call a bounce and wiggle lab. There's, different polynomials of different degrees that you were working with, but you should start to see some patterns after a while. For instance, if you have a polynomial of even degree, what kind of pattern did you see when you look at the graph? Yeah, a parabola, kind of a U shape. Now, the root of this graph, where it actually touches the x-axis, is at x equals 0. That's the only solution. That's the only place that this really touches the x-axis. And what I want you to notice about what happens when you have an even numbered degree for your polynomial is the behavior here. And it's what I call a bounce. The graph bounces off of the x-axis and then returns the way it came. So if it started out above, it's going to touch the x-axis at 0 and then bounce off and again return above the x-axis. Same thing here, here, etc. And then it'd be also true if I had y equals negative x squared or y equals negative x to the fourth that have an upside down shape but only touch the graph once here in a little bouncing fashion. Now kind of an odd one in all this is at x equal 1. The graph doesn't bounce or anything like that. It just goes straight through. So this is one of 3 different types of behaviors you're going to see when you look at the graphs of polynomials. That is, these graphs will touch the x-axis in various ways. It could bounce, it could go straight through, but then we got something else that's going on when we have these odd degree polynomials. So to continue with our really technical math terms, we've got bounce, straight through, and wiggle. So we're going to call that one a wiggle. And that's characteristic of the behavior of a polynomial near an odd root. So this is x equals 0 to x equals 0 is a root 5 times. So it's a root with multiplicity 5. And you get that wiggle kind of behavior. That wiggle behavior is going to be true anytime you have a root with an odd degree, greater than 1. So 3, 5, etc. So bounce, wiggle, and straight through. Those are our different possible combinations when we start looking at these things. So let's see if we can't try and do some predictions then. Let's look at some of the functions on the back of our handout. And first of all, look at the roots. And then their multiplicities. And then finally, we'll make a guess as to their behavior. So let's take a look at this first binomial. What's the root of this binomial? Where would this actually equal 0 if I was setting it equal to 0? Yeah, let's start with the first one at 2, right? So we have a root to 2. Now that root to 2 is to the exponent of the first power, so its multiplicity is 1. Now if you have a multiplicity of 1 or a degree of 1, what kind of behavior do you expect near that root? Straight through. So I'll just kind of be brief here and visit it, abbreviated as ST, straight through. Let's take a look at the other one. The root here is at negative 2. What's the multiplicity of this root? 2. So if you have a root with multiplicity 2, what kind of behavior is that going to have? Yeah, it's going to have a bounce. So let's label our roots and see if we can't figure out what the graph of this looks like. So I got a root at 2. And then I got a root at negative 2. Now at at negative 2, the graph has a bounce. And my guess is that the behavior of the graph is going to look like this. Up here to the x-axis, it's going to hit the -2, and then it has to bounce. So that means it's going to return back the same way. But then it's going to come up and go straight through here, straight through the other graph, or straight through the x-axis at x = 2. So you've got a bounce and a straight through. And that's my guess as to what the graph looks like. Now you can confirm these things by looking at Desmos or your graphing calculator. I mean, either one should give you a good confirmation of what that graph looks like. So let's try it here. Y = x - 2, and then x + 2 squared. How'd we do? Pretty good. What we were looking for is the general shape, and I think we got that. So, nice. Let's try another one on the same handout. This time we've got roots at 2 and -2 as before. So let's take a look at our roots, multiplicity, and then behavior. So I got a root at 2. What's its multiplicity? So what's its behavior going to be? Bounce. And then a root at -2, which also has a root or multiplicity of 2. It's going to be another bounce. So I expect 2 bounces off this one. Well, let's see what that one's going to look like. So a -2 here and a 2 here. What's going to happen with this graph is that if I start out up here, I come down and bounce off the x-axis, and then I got to come back down to the x-axis again. After bouncing off of it, I got to turn around, come back down. What happens when I hit the x-axis at x = 2? Bounce again. And I get this kind of a shape. And again, that's rough and crude, but it's actually got to be pretty accurate. You do have to have some kind of behavior like that. It's going to be pretty easy to check it on Desmos. All we have to do is rewrite this function. Let's put a 2 up here. And there it is. So let me zoom out a little bit. Yeah, the graph crosses the x-axis at x = 16. So, nice. Let's try one more on this handout, finish it off. That is down here at the bottom. So, same kind of chart, root, multiplicity, and behavior. So we have the same 2 roots as before. We've got 2 and -2. How about their multiplicities, though, on this one? What's the multiplicity? This one's a little different. Good. It's not written, but it's understood to be a 1 and a 3. So what kind of behavior does that give us on the graph? A straight through and a wiggle. Okay, so again, let's put our numbers up on the graph. 2 and -2. And I think I've got a point down here just to kind of help you out if you wanted to draw this. I think that's what that's for. But let's figure out what's going to happen at the graph near x = -2. So let me start up above here. And if you're curious, how do I know where to start? We haven't discussed that part yet. So don't worry, don't feel lost. But let's start up here. What's going to happen when I hit this root? It's going to wiggle through. So it means it's going to kind of skim the x-axis for a little bit, and then it's going to keep going down. And then it's got to start a path back up to go through the next root. So try and draw what happens when it goes through the next root. Try and finish off your graph. It goes through this point here, then it's going to curve up. What's going to happen when we go through the x-axis at x equal 2? Straight through. So with just a little bit of information, just looking at the equation, boy, you've got a really good image of what that graph looks like. And again, let's kind of compare this to Desmos. So I'll make this a 1, and I want to make that a 3. And all right, this graph's a little bit deeper, so let me let's go down to say -50, and then on the x-axis I don't need to go out as far, so -4 to say 4 should be good. All right, I think we got the general idea. I think we hit it pretty good. I mean, obviously there's a little bit nicer, but we didn't put a whole lot of effort into graphing this, did we? We just kind of thought about it and said, oh, well, yeah, 2 and -2, and thought about the behavior. So we're doing pretty good for as little effort as we put into this graph. So this is something that I want you to be really comfortable with, is knowing what the behavior of these functions is near those roots. Being able to kind of predict what those are going to be like. In fact, eventually we're going to be able to work backwards. Now, one of the questions you might ask is, well, how did I know it started from up here and not from down here? I mean, I could have equally had, drawn a graph that started here, wiggle through, and then straight through here. Basically the flip of this graph. That's a good question. And that's what our second handout is for. So everyone should have the second handout. It was kind of hinted at a little bit in terms of this graph. You can kind of see the same behaviors again and again. When you have an even function, then as you move out the graph to the right or to the left, both of these tails point up. The graph eventually is going to point up. Now that's when you have a positive coefficient. What if I had a negative coefficient? What if I had y equals -x squared? What's that graph going to look like? Yeah, it's going to be the flip of this, right? It's going to be a graph that points down. But again, both of these, what I call tails of the function, point in the same direction. And that's what you see when you look at even degree polynomials, is that eventually, for an even degree polynomial, both tails point either up or both tails point down. So the degree of your polynomial gives you a lot of information about the graph. It tells you what's called the end behavior. What happens when the value of x gets really, really big or really, really far out towards negative infinity. Big in the negative direction. So that's for an even degree polynomial. If you have an odd degree polynomial, are the tails of the function pointing in the same direction? No, they're pointing in the opposite direction. One heads off towards positive infinity, the other heads off towards negative infinity. If I were to flip this around and look at y equals -x cubed, then I'd have something that looked like that. Again, for your odd degree polynomials, these tails are pointing in opposite direction. So if you have a positive leading coefficient, then you're going to get tails like this, down to the left and up to the right. And then negative leading coefficient gives things the opposite spin. So that's this is what's called the end behavior, and we'll use it to work on the second part of this, or the second handout here. Okay, so let's start with this graph down here. Let's take a look at the end behavior of this graph. Is this graph going to be an even degree polynomial or an odd degree polynomial? Odd. So, you know what? I think these are, I think I should use this for a different example. I think this is problems 10, 12, and 14, etc. You know what? Let's do one this way. We can reverse engineer what this polynomial is. So let's take a look at the roots. It has roots at x equal -1, x equals 0, and x equal 1. Now look at the behavior of the function near these roots. What's the behavior of the function near those roots? Is that a wiggle? They're all straight through, right? They're all straight through. There's no bounce, there's no wiggle. This one's a bounce, that one's a straight through. Let's see, do I have an example of wiggle? No, I don't have an example of wiggle here. All right. Now, if x equals -1 is the root, the factor is x plus 1. That's what corresponds to that. What's the factor that would correspond to x equal 1 as a root? X minus 1. And then x equals 0 just corresponds to an x. So my polynomial is going to be, let's do it in this order, x times x plus 1 times x minus 1. So you reverse engineered your polynomial. Now how do I know that these are all to the first power? Because of the behavior of these roots. Straight through, straight through, straight through. You can FOIL this out and you'll end up with x plus 1 times x minus 1 is simply the difference of squares. So overall you'd end up with x cubed minus x. Turns out that that's actually going to be one of the graphs for some of the early problems. Let me see if I can't find which one. Yeah, it's kind of like problem number 9. Let me see here. Yeah, it's kind of like problem number 9. Okay, let's keep going and play around with some of the end behaviors a little bit more. Let's see, do I want to... 1 second here. Let me take a quick look at problem number 20 first. Skip that one. Yeah, let's play around, like I said, with the end behaviors a little bit more. Let's look at problem number 26. No, this is 3.2. So problem 26 gives you this polynomial. P of x is negative of x plus 1 squared times x minus 1 cubed times x minus 2. So let's figure out a few things about this polynomial. In particular, what would help us and tell us a lot is if we figured out where it crosses the x-axis. That is, where it would equal 0. So its zeros or roots is where we're going to start out. What are the roots of this polynomial? Where would it equal 0? Good. -1, 1, and 2. So those are the roots. Let me just write down, for sake of emphasis, the corresponding factors. The factor that goes with is x plus 1. This goes with x minus 1. And this goes with x minus 2. We don't necessarily really need that for this problem. But I want you to get comfortable with the terminology. Here's your root. Here's the corresponding factor. But what's going to tell us a lot is the multiplicity of these roots. What's the multiplicity of those roots? 2, 3, and 1. Great. The total of that is 6. And that tells you the degree of your polynomial. Degree. If you multiply this out, and boy, it'd be pretty ugly calculation to multiply that all out, you'd get a degree 6 polynomial. Oof. Okay. Now the interesting part, the behavior. What's the behavior of the function near these roots? Good. Bounce, wiggle, and straight through. Now before we graph this, we got to figure out one more thing. This is an even degree polynomial, so okay, that's great. But is the end behavior going to be both of these up or both of them down? Which way is it going to look? Here or here? Down. Why down? Yeah, because of the negative out in front. So both of them are going to face down. So let's flip over our handout, the back side. And we should have some room there to graph this. And I've kind of already started drawing some of this for you. I've drawn the tails. And we figured this out because we knew that this eventually faced down. So try and sketch in the tails for yourself. Or no, try and sketch in the stuff in between. But use what you know about bounce, wiggle, and straight through. So I would start by labeling all your x-intercepts and then trying to connect things so that you have a nice continuous function. So my x-intercepts were at -1, 1, and 2. So let's draw those first. -1, 1, and 2. And start from one side of the graph, pass through this point, using what you know about the multiplicity, and then through this point, and finally through this point. Okay, so at -1, I got a bounce. So when I come up here to the x-axis, I better bounce. And then it's got to dip for a little bit. If you want it to be really, really accurate, then I think the graph's going to pass through the x-axis at -2. Not 100% sure about that one. Then it's got to come through and kind of wiggle through. like that. But the graph should kind of ride the x-axis for a little bit and cross from one side to the other. But it should be a distinct behavior from the bounce. There's your bounce, there's your wiggle through. And then the last one is straight through. So she goes straight through and join the tail here. We predicted these tails based on the end behavior of the polynomial. We had an even polynomial with a negative leading coefficient. So we knew that both of these tails had to face down. And the rest in between we just kind of joined. So without even picking up a graphing calculator, you get a lot of information about this graph. Any thoughts or something you'd like me to discuss regarding our conclusions for the graph of 26?
I tried plugging it in and it didn't graph the way I expected.
Let me try it in. Well, tell you what. Since you're going to be working with graphing calculators at home, let me not always rely on Desmos. And if you ever want to see something on your graphing calculator, then let me know. So let's put this in. So I want the negative parenthesis x plus 1 squared, and then parenthesis x minus 1, right parenthesis raised to the third power, and finally x minus 2. What I would suggest is that we kind of copy the window that we see here, and that is going from, well, let's call it negative 2 to 2.5 on the x-axis, and say about 2 down to negative 21 on the y-axis. So from negative 2 to 2.5 on the x-axis, and y min negative 22, y max say, well, I'll go up to 3. Okay, so we weren't too bad. At least what I got doesn't look too bad compared to what we drew on our handout.
How do we know how far we're going down or
Right.
You know, that's a great question. You don't, unless you start plotting points. But I'm not, I mean, look, mine was much taller than I should have drawn. That's okay. What I want to see is the right shape here. So what I'm looking for is a wiggle here, a bounce here, and a straight through here. That's what I want to see. And then the proper end term behavior. Now, just FYI, I'm not going to be putting this end term behavior on your test. All right? You should know that one. But this end term behavior is pretty spot on. Let me demonstrate that with problem number 46 after I finish anything else on problem 26. Any other questions on 26?
You said you're not going to test us on like wiggle bounce and stuff?
No, that's exactly what I'm going to test you on.
No, I mean
Bounce, wiggle, and straight through.
asking us like, is this graph
You know, this actual point, I mean, that would be a different question. If I was just asking you for a rough sketch, then this is fine. I mean, my idea, my philosophy is that I don't really want you plotting points. And look, we got wonderful graphing calculator software on Desmos. You've got a graphing calculator on your lap. So I don't need you to sit there and plot points. I want you to understand the big ideas, the big picture. I want you to understand, roughly speaking, what this graph is going to look like. I mean, if this graph was your profit function for some company, you should just be able to look at that and go, gee, I'm worried. This is eventually going down, all right? That's the big picture conclusions you should be able to come up with. Or, you know, where is this going to hit the x-axis? Where am I going to be breaking even? Those kind of questions. It's when you get into calculus that you can actually do some calculations to find that point. Right now we can find that point, but you just have to use the calculator's capabilities of finding a maximum. Hits the second key and the trace key, you can find a maximum there. So we can still do that. All right, I wanted to demonstrate to you a little something about the end behavior of these polynomials. So let's take a look at problem number 46. And you can follow along in your graphing calculator. I'm going to do things up here. So if you want to graph these two polynomials, that's great. Problem 46 gives us two equations, and they want us to graph them the same way, or in the same window. So the first one is y equals negative 1/8 x cubed. So I'm going to be lazy and just do negative 0.125 x to the third power plus 1/4 x squared, so plus 0.25 x squared plus 12x. So let's take a look at what that graph is. And you see, in fact, we could do some factoring and figure out what that graph looks like, and that's fine. So you get some crazy behavior here. Now they want you to compare this to the graph of y equals just that first term here. In fact, let me just do this. So let's copy it there and paste it in here. Let me change the color. There we go. Make that one red. Do these graphs look the same? Not really. Not too much. But that's because we're close in to x equals 0. We're close to the y-axis. Take a look at your handout. Both of these graphs are graphed with a wider view. And if we look at those graphs on the wider view, is there much of a difference between these two graphs once you get far out away from the x-axis or away from the y-axis? So my artificial zoom here. Those graphs look pretty much the same, don't they? There's not a huge difference between these two. And that's because they have the same end behavior. They're both odd functions, so that means the tails point in opposite directions. Because there's a negative, then we go up and to the left and down and to the right with our end behaviors for the odd function. But if you use this viewing window, you're going to see that these two graphs are pretty similar. And that's the idea behind the end behavior, is that eventually, after you move away from the x-axis, things settle down. That's because those leading terms really dominate. And the rest of the terms just don't really matter. Let's try some more here. Let's try problem number 10. And I think we can use our handout for problem number 10. So the equation in problem number 10 is q of x equals negative of x squared times x squared minus 4. Let me factor that a little bit more. What can you tell me about x squared minus 4? Thank you. Exactly. X plus 2 times x minus 2. What are the roots of this polynomial? How about a different voice? A voice I haven't heard from in a while. Matthew, thanks for volunteering. What would the roots be? Where would this actually equal 0? Not a 1. 0. Yeah. So it's 0. That's a root. Keep 2 and negative 2. Good. How about their multiplicities? What would their multiplicities be? Good. 2, 1, and 1. So that gives us a 4th degree polynomial. What's the behavior going to be then? Good. Bounce, straight through, and straight through. Now, we know we have an even degree and a negative leading coefficient. So that tells me I'm going to have this kind of behavior. So do you see anything that kind of matches that? Is there anything on our handout that matches that behavior? I'm thinking no as well. Oh, wait. Time out. Let's flip on the back side. We're looking better there? Do you see anything that might match that? There we go. Anything at all? Last call.
The thing in the circle.
Yeah, good job. All right, so this one, good deal. Let's see that it matches exactly what we expect here. So we've got a root at -2, a root at 2, and both of these, as you suggested, would be straight through, and they had a bounce here. We expected 2 tails that pointed down, so wow, it's got everything. Perfect. All right, let's try that one again, except with a different problem. Problem number 12. Oops. So problem number 12 is s of x equals 1/2 times x to the 6th minus, 2x to the 4th. Okay, so a little bit of a pain here, but here's what I'm going to do. I'm going to factor out the GCF, and I'm going to factor out that 1/2. Just want to get rid of it. It's kind of annoying. So what's part of the GCF? How many x's can I take out? X to the 4th. Now if I factor out a 1/2, that's going to be dividing by 1/2. That'll cancel out there. What's 2 divided by 1/2? 1. So it's going to be x squared. No, 2 divided by 1/2 is going to be 4. So x squared minus 4. And how are we looking on there? That looks pretty good. I guess we can factor it a little bit more. X to the 4th, x minus 2, and x plus 2. So do the same thing. Try and take a look at the roots, their multiplicity, and then their behavior. See if you can't find a graph that matches all of what we need here. Okay, so what are the roots? 2 and -2, all right. And 0. Still have a root at 0. What are the multiplicities here? Ruta? Good. 4, 1, and 1. Now notice that that gives me a total of 6. So by accounting for the roots and their multiplicities, I should always match the degree here. This was a degree 6 polynomial. I've got 6 roots accounted for, so I'm all set here. Behavior. Bounce. Straight through. And straight through. Is there one that satisfies this one? Anyone? Anyone? Any guesses at all? No? Still confused? In French, you'd say "Je suis ici." I am here. Estoy aquí. In Spanish. Say again. So we had a bounce at 0, straight through and straight through. So here's your bounce, straight through and straight through. Notice that the end behavior matches as well. You had a positive leading coefficient here. You expected your even degree polynomial to go up on both ends, and that's exactly what you're seeing here. So yay. So there's a nice correspondence between the behavior of these roots, their factors, their multiplicity, and their graphs. There's a beautiful correspondence, and I want you to be comfortable with that. We're going to sort of slide up to problem number 72 from a different part of the book. We're going to move into section 3.3 and look at problem number 72 here. Let's see if we can't reverse engineer this polynomial. And I'm sorry, I'm not sure what's going wrong. I can't zoom in right now, but let me see if I can't do an artificial zoom. Make this a little bit closer. So they're looking for a degree 3 polynomial that looks like this. Okay. What should you determine first? What kind of things can we take note of? The roots. Absolutely. Let's take a look at the roots here. Well, if it's a degree 3 polynomial and we have end behavior like this, what do you know about the coefficient? Is it positive or negative? It's going to be positive. All right. So let's write down the roots here for a second. Roots. What would those be? Where are the roots in this graph? -1. Is 0 a root? No. So -1 and 2. Now, if those are the roots, then we have to deal with something called the factors. So if that's the root, then x plus 1 is the factor. If 2 is a root, what's the corresponding factor? X minus 2. And then finally, let's work with the behavior and then the multiplicity. All right, so at -1, what kind of behavior do we have? Straight through. What kind of behavior do we have at 2? Bounce. All right, so we got our roots, behavior. Let's next move to the multiplicity. I don't even need to look at the graph anymore. If it's straight through, what's the multiplicity? Bounce is a... Why is this a double check of our work? Right here, we got a 3. Yeah, it asks you for a degree 3, right? We've got it. We've accounted for all of them. So the final polynomial then is just going to be a product of these. It's going to be p of x equals x plus 1 times x minus 2 squared. You should be able to check that. In fact, you can check it exactly. Set up your graphing calculator window to match exactly the window that they use there. So they're going from, say, about -2 to 5 or 4. And then from -3 to, say, 4 or 5 again. So you should be able to double check yourself simply by plugging it into your graphing calculator. That's a great problem. I want to do another one like that. Before we do one more like that, let me ask if you have any thoughts on this one, problem number 72 from section 3.3. All right, I think you guys did good on that one, but it's an important problem to me, so I want to practice it again. Why don't you try problem number 74? Do the same thing. Set up your roots, factor, multiplicity. Try and find a polynomial of degree 4 this time that matches the conditions given there. You can check yourself on your graphing calculator when you're all done. Now, it'll help you to an extent. I mean, I can easily write these so that your graphing calculator isn't really difficult. So I suggest you know the principles. That doesn't look like a bounce. That looks like a straight through. So that goes straight through. This is a bounce. So you got those two mixed up, those last two.
top side of the x-axis, it hits this, and it bounces, it returns. It doesn't pass through, it just goes back the other way. So that's a bounce. This is a straight through. It's on the negative side of the x-axis, and then goes to the positive side. So it's straight through, and that's a straight through. Okay, looks good. 4, good. All right. Looking good. Looking good.
Okay, so as far as our roots are concerned, we have roots at -2, at -1, and at 1. The corresponding factors are x plus 2, x plus 1, and x minus 1. Let's look at the behavior of these roots, or at these roots. So the behavior here is straight through again, and the last one's a bounce. So the multiplicities would be 1, 1, and 2. And that's nice because they asked us for a degree 4 polynomial. We've got all 4 degrees accounted for. So just multiply together these factors with these exponents. P of x is x plus 2, x plus 1, and x minus 1 squared. Beautiful. How'd you do on that one? Pretty good? All right. Is there anything else that you might have that you're not sure of regarding this problem? All right. I think I just want to do one last tiny one from section 3.3, and then we'll be done. Or actually 3.2, and we'll be done with that one. And it's problem number 36. They ask you to graph this and express it in factored form, and then sketch it. So let's look at problem number 36. This is still 3.2. This is our last one for section 3.2. So for 36, our equation is P of x equals x to the 5th minus 9x cubed. Factoring it's going to be really, really huge. Once you get it factored, you know where the roots are. And if you know where the roots and their multiplicities are, you know what the behavior of the function looks like. So suggestions as to how to factor this one. Factor out an x to the 3rd, which leaves by an x squared minus 9. Are we done factoring that one? X to the 3rd times x. Perfect. X plus 3 and x minus 3. Let's create ourselves a little bit of a chart here. So we've got the root, multiplicity, and behavior. So I've got roots at 3, -3, and where else? 0. So the multiplicity at 3 and -3 is 1. What's the multiplicity at 0? 3. What kind of behavior do I get near these roots? Yeah, a wiggle. All right, not too many wiggles for us today, but there's a wiggle, straight through and straight through. This is a degree 5 polynomial, positive leading coefficient, so we expect tails that go in opposite directions. So kind of at a really rough guess, so eventually this graph goes down to the left and up to the right. That's what we know because it's an odd degree polynomial with a positive leading coefficient. So that's what the end behavior of this graph tells us. Now I need to fill in some roots. I got a root here at -3. I got a root here at +3. And then a root here at 0. So I need to connect the dots in an educated way. So let's start with the end behaviors. And these are just guesses, aren't they? I mean, am I really plotting points? No, I'm not. I'm not sure why this has gotten quite so dark. All right, so when this comes up to the x-axis at x equal -3, what's it going to do? It's going to go straight across. And then it's got to come back down and touch 0. What kind of behavior am I going to have near 0? Wiggle. So that's not bad. That's terrible, really. I've come back on itself. I had to. Yeah, I got to wave instead of... Yeah, I failed the vertical line test. Oh, I really failed this one. So, but this one's going to wiggle through. So it doesn't go straight through. It kind of curves its way through. And it's got to bend down. And then we're going to get back up here. At x equal 3, the graph's going to go straight through. All right. So other than the fact that I miserably failed the vertical line test, that's roughly what the graph should look like. For homework, this is section 3.2. Try 5, 9 through 27, 31, 37, 45, 53, and 59. It's really not all that much, I don't think. I hope. I don't want to overburden you, but you need to get enough practice on this. Okay, let's take a break. I'll see you in about 7 minutes.